All right, the next topic in differential equations that we want to look at is called separation of variables. And it's a nice technique. It doesn't work for all differential equations to find the solution. And remember, what's happening is you have some type of an equation that has derivatives in it, like y primes or whatever, and you want to find a solution, an original y equals or f of x equals that will satisfy that differential equation. So separation of variables, when it works, is real great. And here's what it deals with here. It says some first order differential equations, which are when it says first order, it means that the sort of the highest derivative that you see is the first derivative, can be solved if you separate the x's and dx's from the y's and dy's. So where in the world are the dx's and the dy's coming from? Well, from the derivative, y prime or dy dx. All right. So this is the procedure of separation of those variables. So here's the little note. Y prime is the same as dy dx, as you know, and we'll be separating the dy from the dx in these problems here. All right. So let me scroll on down. All right. Here's our example problem. For the differential equation y prime or dy dx equals x squared over y squared, part A, we want to find the general solution, so y equals, whatever, and then in part B, we want to find the particular solution that will satisfy the initial condition that y is equal to 2 when x is 0, okay? Or that goes through the point 0, 2. All right. So first off, take our, I'm going to move me down here a little bit. Take your y prime and make that dy dx equals x squared over y squared, and that's what we have right here. Let's move it up a little bit. Okay, so at this point, on the left side I have dy's and dx's, on the right side I have x's and y's. What I'm going to do is to, in this case, cross multiply would work. So I'll multiply the y squared by the dy and the x squared by the dx. Sometimes you'll have to do it a different way perhaps, but that's going to work in this case here. So now I have y squared dy equals x squared dx. And let's integrate both sides. Let's integrate both sides of the equation. Integration is just an operation. Whatever you do to one side, you do to another side. And if we integrate y squared, and I have dy, so I'm integrating y's with respect to y's, x's with respect to x's. It's perfectly set up. Integrating y squared is just a power rule. So I'll go y cubed over 3, or 1/3 y cubed. Now, it is an indefinite integral, so normally you get a plus c. I'm just going to put the plus c on the right side, okay? And when I integrate the right side, it's very similar. This will be x cubed over 3, or 1/3 x cubed, and I put my plus c. In this particular case, I'm putting a plus c sub 1, which you might see why here in just a moment or two. All right, so I'm going to try to solve this for y if I can. I'm going to multiply both sides by 3. I'll get y cubed equals x cubed plus 3 of these arbitrary constants that we're calling c sub 1. All right, so now at this point, what I've decided to do is, instead of having 3 times some constant, which we call c sub 1, why don't we just make that c, just a plus c. All right. And then I want to get y. I have y cubed, so I'll take the cube root of both sides. And now my general solution to the differential equation right up in here is that y is equal to the cube root of x cubed plus c. All right. Now, in part B, we're going to use this initial condition to find the particular solution, which basically means you're figuring out what c has to be so that the equation goes through this point here. So here I know that when x is 0, y is 2. So I'm going to take my general solution and plug in 0 for x, 2 for y. So there's the 2. There's the x goes into here. And I'll get 2 is equal to the cube root of 0 cubed, which is 0, plus c. So 2 is equal to cube root of c. Raise both sides to the third power, and you'll find that c is actually 8. And once you have c is 8, plug it back into here, and then you have your particular solution. Y is equal to the cube root of x cubed plus 8. General solution, particular solution. All right, let's take a look at another one right here. Different differential equation. It looks more complicated. dy dx is equal to 6x squared all over 2y plus the cosine of y. Now, we don't have any initial conditions here, so if you don't have any initial conditions or extra information, just find the general solution. So we're going to see if we can separate the variables. So I'm going to multiply both sides by 2y plus cosine of y and multiply both sides by dx, which should be equivalent to cross multiplying in this case. So now I'm going to have the 2y plus cosine of y in parentheses dy equals 6x squared dx. I've separated the y stuff and put it with the dy stuff. I've got the x stuff with the dx stuff. All right. Let's go ahead now and integrate both sides. And when I integrate the left side, I have two terms. The integral of 2y is just going to be 2y squared divided by 2, or just y squared. The integral of cosine of y with respect to y is just sine of y. I'll put all the plus c stuff on the right side. Integrating 6x squared would be 6x cubed divided by 3, or 2x cubed plus the arbitrary constant c, which we put on right over here. Now, sometimes what's going to happen is you're going to have an incredibly hard time, if not impossible time, of solving this for y. Because if I try to solve for the y squared part, then the sine of y goes to the other side. If I try to solve for this y squared goes to the other side. So sometimes you'll just have to leave your solution as you see here. I mean, we like to solve for them, but sometimes you can't solve for it. So we can't write this one as y is equal to some function of only just x in this case, and that's fine. And remember, we don't have any initial conditions for this one. All right. The last problem looks like this one here. Let me move this down just a bit, or move it up. There we go. So we're going to solve the differential equation. In this case, y prime is equal to x squared y. So the first time we have not had a fraction on the right side. So we'll make y prime dy dx, and that's equal to x squared over y. So this time I'll multiply both sides by dx to bring it over with the x squared, and then divide both sides by y, or multiply both sides by 1 over y. If you do, you get the y stuff with the dy's and the x stuff with the dx's. All right, so now we've separated all the y's and x's. Now we'll integrate both sides. So I'm going to integrate the left side, integrate the right side. When I integrate 1 over y, that's the, with respect to y, dy, that's the natural log of the absolute value of y. So that's your integration rule for that. On the right side, when I integrate x squared, I'll get x cubed over 3. And we'll put our arbitrary constant plus c over here. All right, now, this one we can solve for y. So I want to get rid of the natural log, so I'm going to raise both sides. Actually, I'm going to use a base of e and this is what I'll get. I'll get e to the natural log of the absolute value of y on the left side is equal to e to the x cubed over 3 plus c power here. And that allows me to get rid of the natural log over on the left side. So now I have the absolute value of y is equal to e to this kind of complicated power. But if you have e raised to the sum of terms, then what I can do is kind of change that out, kind of go backwards. I'm going to make that e to the c times e to the x cubed over 3. Because remember, if you're multiplying and the bases are the same, you would simply add the exponents. So I'd get c plus x cubed over 3, which is exactly what I had up here. All right. The reason why I do that maybe is because e to the c is really just some other constant. All right. E is a number, c is going to be some number, I just don't know what it would be. I don't have any initial conditions. And so that's what I have here. Now, the one slightly tricky thing to look at here is, all right, that's what the absolute value of y is. And without knowing any other information, I don't know whether y is going to be positive or negative. I know the absolute value would make it sort of positive, but what goes inside here, okay? So what we can do is say that, well, y is going to be either positive e to the c times e to the x cubed over 3, and if it is, the absolute value just makes it positive, or y could be negative e to the c times e to the x cubed over 3, and if it goes inside the absolute value, it would make the result being this positive thing we have here. So here's a case where you did not have any initial conditions, and this is your general solution that you have here. So hopefully you find that it's not too bad when you are able to take a first order differential equation, which means only a y prime in it, and if you're able to separate all the y's with the dy's and the x's with the dx's, then we can integrate both sides and work toward our solution that way.